Right, welcome to the second experiment, Year 12. This is the start of Chapter 2. This is starting to study about materials, and we're going to start with the ideas of Hooke's law. So what I've got here is the second experiment, and it's really important in terms of skills, so I'll cover that in a second. But the basic idea is, in the course, we know that you know about Hooke's law, how much this stretches, this spring that I've got here, but when we start putting springs into series and combinations, so series combination, different combination here is parallel, so side by side, then we start to get different behaviours, and you can see that just in terms of how they react. So we're not going to be doing timing, but it does give you an idea of the stiffness of the spring. So this is really stiff, it gives a lot of force to make everything accelerate. This one's quite slack. Yeah. So what we're going to do is we're going to do static stretching. So we're going to add weights, we're going to change the length, we're going to find out Hooke's law from it. We should, as long as we do not exceed the elastic limit on these, we should get lovely straight lines. And the aim of this experiment is to get the straight lines for series, single, and parallel springs. Now these are all about the same springs, they're all about the same spring constant. So when you start to join them together, the forces act differently to when they're on their own and when they're side by side together. So this very much builds on the skills you need in terms of the practicals that we're going to do. So although the actual science is about things like Newton meters, which is the basis of Hooke's law if you think about it, because when you look at the scale, it is nice and linear, and that's telling you how much longer the spring inside gets when you add more force. But what I want to concentrate on is how you record data. So in the student practical book, in section 2, which is recording and presenting the data, really want you to make sure you read through here and get things nice and clear, because some people's results from the last practical aren't very organised, they're not tabulated, they need to be in a table. And just to be clear, almost everybody does this, but the table goes down, so your columns of data. And the reason is then you can start to see patterns. If you just put them in on the page without a table form, without putting them into a table, you cannot see patterns. You also cannot see patterns if you don't do the results in order. Okay, so we're looking for the skills that results are taken systematically, so there is a pattern going down, and they're actually recorded systematically too, so accurately and so on. So titles need to be clear. They don't need to be long, but they definitely need to be clear. If you put length, for example, length of what? Length travelled, length of spring, length, whatever the experiment is. So be clear with your titles, and the recording of the units is done with a slash. Okay. Now, stuff that you should have done at GCSE is simple ideas in that your independent variable, the one that you are changing, that does not depend on anything, goes down this left-hand column. That's always your first column. What we then do is the column that depends on that, the results from changing this, comes second. So second column is always dependent. Now you may have 2 or 3 repeats, okay, which is good, and an average for those repeats, but it's still independent followed by the dependent. And your final dependent value, the thing that you're trying to find out about, should really be that last column. Now, for this experiment, we're going to have 3 springs. So all I want is the extension. And how do you get extension? Well, you measure the length. Okay? But what I'm actually after is the extension, not the length, because the graph will be really hard otherwise. So we want to know the x that's in the equation, and so I'm going to need you to write down the data. So we are going to have the dependent variable 1, and then from that we're going to have dependent 2. Okay, so this case this will be length, and then this will be X. This will be how much stretches. So the first result will be 0, okay, because that will be your starting place. So that will be enough for one spring. Then we've got a second and a third. So basically you'll have 3 tables, but don't do them separately. Just do them as 3 columns, the second 3 columns, the third 3 columns. That's how to write up a set of data, because then you can compare it across. The fourth column, okay, what we're actually going to put down here, will be actually the same for all of them. So you only need one independent variable. So actually 2 columns, 2 columns, 2 columns. And that will be enough for your first, second and third experiment. Okay, first, second and third. So the other important bit is actually looking at the units themselves. Our masses are, and I don't know if you can see this, but they are 100 grams. But is that exactly 100? Well, if you take the results, you measure a load of them, what you'll find is they are actually just to the nearest tenth of a gram. Now that's quite hard to show how good that is when you're doing your readings, because it's not a good unit. So instead of saying everything is to the nearest tenth of a gram, plus or minus 10 grams, if we put it into kilograms, that will be 0.01. So every result must be recorded to 2 decimal places. Okay? It shows, anybody who looks at your data, it shows them how precisely you've measured that. You know, was it about 1 Newton or was it exactly 1 Newton? Yeah? So how many decimal places depends on the equipment you're using. So all of your readings, when I look at them, even if it's 0, should be 0.00. Okay, so all your readings need to be for lengths and for extension X need to be 2 decimal places. Okay, on your graph you'll be able to get 2 decimal places, so that's kind of crucial. That's what makes it all work. So I'm going to finish recording the video section, and what I'm going to do is just put different masses on. I'll put them all the same each time, and we'll start off with 100 grams, go up to 800 grams, and sorry, 900 grams. And what we're going to do is I'll do close-up shots of each of the springs. Okay, so you can record the length, but you'll need to work out the extension. And then what you're going to do is plot all 3 as lines on the same graph. And because they will all start with extension 0 as the very first reading, then what you'll find is that they'll all start in the same place and they'll all fit on the same graph. The aim for the actual result, the final answer in your practical, is I want you to show me how these relate. Okay, how these 3 springs relate. So I want you to find the spring constant for each of them. Now from our session today, that's on Wednesday, we had F equals kx. Well, if you plot the force produced by the spring, okay, the force up the side, and you put the extension along the bottom, then when you get the gradient, that gradient will be F divided by x, so that gradient will equal the spring constant. So you'll need 3 gradients to find 3 spring constants for 2 in series, 2 in parallel, comparing them to the one in the middle, that will be just the one spring constant on its own, k. Okay, so what you can do is you can find the value for k, you can find the value for this k, the combination, and this one, and I want you to see how that compares. When you did this in GCSE, you should have been taught to measure it with accuracy, so you know that you're not going to measure the spring, because when you measure the length of the spring, well, it changes shape, so you can never get an accurate value. Huge amounts of uncertainty in it. So what we're going to do is we're going to take our spring and measure the position of it, the position of the points and how it changes as we add more and more force. So I'm going to start off with this initial mass, but this is our 0 reading. And what we're going to do is we're going to measure that in terms of its position. So if we take this fixed bottom to it, it's not going to change shape, but we can measure it off the scale there. So we can find the 0 value for this position. And then what we can do is compare how that position changes as we add forces. So as we stick a second disc on, it's going to go down, obviously. So each disc on top is going to be an additional 100 grams, but you'll need the force, so you'll need its weight, which of course is nice and simply mg. Now on your table, if you put load in newtons, rather than writing it down 100 grams, 200 and so on, actually work it out in kilograms multiplied by 9.81. So again, our calculation was 2 decimal places, so you can actually get your answer there to 2 decimal places. So we're going to compare that position against something fixed, and if we move back, then obviously you can see the jig, the frame is rigid and the desktop is rigid, so we're going to take all our measurements from the desktop, and we'll do that for all 3 of the setups. Okay, this is the second setup, so this is the one spring on its own, and again using the same position, this is our reference point, that is our zero force. Okay, additional force only from this point onwards. And third set of data, this is for our parallel springs, or springs in parallel. The bridging between them means that they're both roughly equally loaded, but it doesn't matter too much because this effectively does the average. So even if that one stretches slightly more and that stretches slightly less, it will automatically average out the weights.
Okay, when you get to the end of your experiment, you should end up with 3 lines like this, and you need to work out the gradient. Your key skill is actually getting a line of best fit. So once you've got your data for one set of results, I suggest you do your line of best fit on that, then plot the second set, do your second line, then plot your third set and do the third line. All of those should then, even if they're a bit scattered, they should then give you your best value that you can, your average for all the results. Okay, so all 3 of those, plot them, make sure they're nice and clear, show clearly which plots are which. You might want to do them in slightly different colours, so red crosses on your graph, green crosses, blue crosses, whatever. But if you put them on, you'll get your 3 values for K simply by saying how much. If we put a line down, they'll have the same extension, but you can work out how much force it took to extend that much. Okay, so it's force per X, so force per unit length. So if you're basically saying how much force to stretch each spring a meter, that will be way off your graph, but that's what you're after. Okay, at the end in your write-up, I want again to show your calculation so we know how you got it, but most importantly is the detail in the graph, units, just the same as before, and extension also needs units. So again, don't do in brackets if you've learned that. What you're after is in meters, something like that. Okay, if you want to do it in millimeters, it still works. If you want to do it in centimeters, it still works, but easiest, get into the habit of doing the most convenient unit. Millimeters, I suspect, is probably best.